I'm going to talk today about that completely delusional idea of data science in production. A little bit about me. These are my bragging rights of why I'm here, I guess. So, I mean, I'm a data scientist by profession for a while now, but you know, I'm much more also a techie, a geek, and an innovator with passion. That's what drives me. I had a successful startup. They're called AnyChange. They're now like the biggest comparison website in Japan. Feels very like coming full circle because the first prototype we showed investors was a rip-off of USwitch, which belongs to ZPG. I have a PhD in mathematics. I mean, with an audience full of data scientists, that's not impressing you. I feel like the only people I impress with my PhD are my parents. And I'm now leading data science here at Zoopla. I started to publish blog posts on Medium, so feel free to follow me. There's some good content there and more to come. So I hope you all know Zoopla. I mean, you all know Zoopla. We found Zoopla, like literally. But I hope you also used it maybe in the past. But Zoopla is a property portal. It's a marketplace for consumers looking for properties to rent and to buy, and the agents who basically manage all that. And when it's really quick. Don't want to bore you too much, but basically, if you look at Zoopla, it's like big data and big opportunities. I mean, that's why Zoopla got into the data science business. We have like over 1 million live listings on our website at every one time, and we get like 10,000 new listings every day. We have 14 million page views. That translates into like over 1 million users. We handle around 3 million property searches every day, and that translates in the end into like 20,000 email leads which go out to agents. We've been around for a while, so our historic listing catalog has 43 million listings, and they all come with images, floor plans, descriptions, prices, etc. And I mean, we have alone 300 million property images for our historic listing catalog. We're second in the market, which means we're big enough to afford data science and hungry enough to make it to spot one. And the only way you can achieve that really is through innovation, and data science plays an important role in that. It's not just me. There's a team behind me. This is the dream team, data science at Zoopla. We're a decent size for like a company, but you know, we're also fairly motivated, so we get a lot of work done. Unfortunately, I'm not going to talk so much about the actual data science projects we're doing, because we try to talk about data science in production today. But just read our blog posts. There's a lot about the projects we're actually doing. But yeah, even if I don't talk about the actual projects, we're like data scientists of the enterprise. What does that mean? It means this. Half of the room laughs, for the other half, it's too close to where it hurts. It's a very typical problem, you know. It's like what data scientists could do or should do, you know, what the kind of people think around you in the business, what you're actually doing all day, and then like the kind of actual day-to-day job. I can underpin that with a little bit of like statistics. Oh yeah. So just January 2019, a survey basically said that 77% of all the businesses report challenges with business adaptation of data science. What that means is that 3/4 of all data science projects are collecting dust. Great. If you look at Gartner 2017, they said 85% of all big data projects don't really move past the kind of discovery phase, and they didn't really get much more cheerful. January 2019, basically exactly the same picture. What that means is making data science a success is really hard. And the reasons why are complex, but they're also commonly misunderstood. And that's what I'm going to talk about today. And I think there's a lot of value in understanding that. So no neural networks, but a lot of pretty slides. So if we look back at this 2016, there was some survey. Actually, I couldn't find the original reference, but there was some survey in 2016 which asked some data scientists, and basically 80% of data science, according to that survey, is cleaning, finding, and preparing data. And at the same time, 60% of the data scientists said it's the least enjoyable part of their job. So that became the almost famous 80-20 rule, and I mean, almost every presentation about production always talks about that. And if I just show you like some kind of diagram about the kind of data science pipeline, right, it's fairly understandable where the kind of popularity of the 80-20 rule comes from as a problem statement for data science. So this is called the cross-industrial standard process for data mining. It comes from 1996, so it predates data science as it's today's discipline by a few years, but it's interesting how it is basically a data science kind of workflow. I had to do some changes to update it for like today, so there's clearly more isolated data silos in the middle than 1996, and the importance of the kind of data preparation step clearly increased, if anything. So yeah, it's clear why people talk about, you know, the challenges of cleaning and preparing data. Actually, I'm not stopping here. I need to do some more annotations because that data is usually on fire. And at least in my team, I hear a lot of like angry swearing from the people who currently try to prepare their data for their modeling tasks. But, you know, as appealing that all is, you know, there's another really important thing in this, and that's actually what I started to like focus on a lot. And I'm always surprised how much we focus on that single step of preparing data. If that box there called deployment makes me just go like that, because I mean, you don't just deploy data science. I mean, fair enough, you know, this predates data science, but you can talk to, you know, a lot of vendors today or people who try to address that, and yes, they talk about one-click deployment or deploy within minutes. But if your business wants to be more serious about data science and make that like a core part of their business and not just a value add on the side, production is not just deployment. You can't just deploy models. And if I want you to take away one thing, really one thing of this entire presentation, it's productionization of models is the toughest problem in data science. It's not the deployment, it's not the data preparation, it's production. And I'm going to walk us through a little bit the kind of background and motivation of why that is. So if we look at the actual reality of data science, you know, in production, your model is a living, breathing thing. It's not just traditional software. So it has a kind of model life cycle. Your model drifts. The world isn't static. You need to retrain your model. But then you have no guarantees that your newly trained model will actually be any good at modeling unseen data. So you constantly need to monitor your model in production. You constantly need to evaluate its performance. So that entire thing in production, this life cycle of models, is rarely discussed or really addressed. But that's not enough, because if your data scientists are around a while, they will build a challenger to that production model. So you basically have a second model. It has exactly the same kind of nature. It is alive, and you need to retrain your challenger model when it starts to drift, etc. So we immediately at like, well, we can't just handle lifecycle management. We need to scale it, because at some point you have a challenger. And the next question is, how do we then proceed when we have a challenger in production scoring happily, and how do we evaluate the performance versus your current production model? And what you see a lot is like just a traditional A/B test. I mean, it's been around for long enough. It's a kind of a easy go-to. We just run a A/B test. So if you assume you have some kind of smart traffic splitter, you just send 10% of your traffic to your new challenger model, and then you just like run that for a while, and then you just evaluate performance. But there's a question there. It's like, how do you compare model outputs and evaluate their performance if you only see the output of one model? That's important when you, for example, look at a recommendation engine where what I recommend you is highly dependent on you as a user and your previous interactions. So how do I compare the output of these two models if I only see the output of that one user from one model? It's really difficult. And not just that, there's another question. What happens when your challenger model isn't actually that good, and the reality looks a little bit more like this? What that means is 10% of your users just had a bad experience, and they end up being very angry with you. And if your users are not angry, there will be some manager in your business who's angry, who looks after a KPI you just destroyed. So not a great way to test the performance of a challenger model. That clearly needs to be like a better way. And we're not really done, because the data science reality looks much more like this. If I wanted to keep this slide updated, I probably had to add a framework icon every day to this slide. I mean, the data science is extremely complex, and putting that into production gives every IT department a pretty good run for their money. So if we summarize like the problem statement and like the requirements we have as data scientists in production, we want to evaluate really big numbers of incumbent and challenger models in parallel. We want to manage the model lifecycle. We want to handle the increasing complexity of data science toolkits that data science field is like moving so quick. One thing which is really, really close to my heart is like we want to allow experimentation in production without impacting the user experience. And that means we need to decouple the kind of business objectives from the data science objectives. The business wants to run a stable experience. Data scientists want to play around with your users and customers. We also need to decouple like enterprise requirements like authentication, SLAs, and GDPR, just another buzzword. It's my SEO optimization, from the actual code of your data science models. I don't want to deal with this. And if you're the size of Zoopla, you need to scale this to like 50,000 page loads per minute at peak time without hiring armies of DevOps engineers. So how do you do that? The solution is called rendezvous architecture, and we all stand on the shoulders of giants. It's not something I came up with. MapR has some extremely brilliant solution architects and engineers, particularly Ted Dunning and Alan Friedman, and they've been publishing the kind of idea of rendezvous architecture in their book, Machine Learning Logistics. And
Python, R, and so on. Why the model is depending on a programming language? I understand that the libraries are available, but theoretically a model is not a programming language independent.
I guess we can keep that question for a little bit later.
Yes, okay.
Like right now, we just take it as a given. So yeah, rendezvous architecture. At its core, there's a really simple kind of concept, and it is basically treat your input data as a stream. That's like the first kind of key takeaway. So when you have requests coming in, let's say from your website, to score some kind of event data, etc., or a recommendation engine has to produce some recommendations, publish this request to an event stream, and then you your model subscribe to it, and you immediately solve for easily distribute a request to a big number of models in parallel. So that's like first requirement ticked off your list. But the main challenge now is like, so okay, we're not done, obviously. We need to like actually respond to that request, and there needs to be something which takes all these output from models and turns it into a response. And easy enough, map R says, treat your scores as a stream, and that makes sense. So basically now, if we start to build a streaming architecture, your models also should just publish their scores to an event stream. And then we have something called the rendezvous process, which subscribes to your original input data stream with the requests and basically meets them up with the scores. And that's why they gave it the name rendezvous process, because the original requests meet their scores in that process. Why would you do that? Because it decouples the ability to respond to a request from your models actually producing any results. Because you are subscribing to the original request, even if all your models go down or are too slow for your SLAs, your rendezvous process is aware of the original request. So you can easily implement some kind of race condition that, you know, if the models are not fast enough for your SLA, send a meaningful default, etc. So it's very important to have this kind of rendezvous process for the ability to basically decouple a response from the performance of models. So if we take all that and we actually translate it into a kind of architecture for data science, it looks a little bit more like this. I will talk about certain parts of that more in detail, but we basically created a hierarchy of like business objectives as we wanted and the modeling or data science objectives. If you have a request coming in, there is something which we talk more about, the rendezvous service which receives that and it publishes it to a business objective topic, and that could be produce a recommendation. There's a microservice which is a data enricher which subscribes to messages coming in and has the ability to call additional external data sources to enrich that original request before it publishes it on a topic for the models. And this is quite interesting because that means you can handle stateful models, no problem. Because let's imagine it's a recommendation engine. You get the event of a click coming in, but obviously we know that when you look at the context of that event in the series of previous clicks, you can improve the relevance of your recommendations. So you can easily have a Redis cache there which just remembers previous interactions and enriches your message with that previous clicks. So you can have stateful models, that's not a problem there. You can also pipe in any other kind of data you might need for scoring. And in the end, everything has like there's a request with the data you need for your models. The models just consume it. So as you see, there's not just a model there, there's also two additional kind of models, which you always need, even if you just have one model. One is the canary model, and the problem is because models are alive, they get constantly retrained, etc. You don't have a constant baseline because you constantly change your models. So you need a canary model which you don't change just to have a consistent baseline to allow you to compare your models against so that you can tell whether something is wrong with the model or something is wrong with your input data. It's really hard to tell if you don't have a canary model. And you should have like some kind of decoy model to just log off all the messages which come in. That's very handy if you want to, for example, replay the last hour of messages to just evaluate a new model, or if your model is stateful, not just with like data it needs, but the model itself, like reinforcement learning, etc., and you want to warm up the model, you can just replay the last hour of production data if you log all the requests coming in. So it's very important to think about these things too if you build a serious production environment. And then basically the models just send their scores back out. If your model can handle 100 requests a minute and you have 200, this is a stateless kind of microservice architecture. You just deploy 2 copies of it, and you just do round-robin load balancing of your requests between your 2 models. easy peasy. So the only challenge is with that rendezvous service. Why is that? Because the entire architecture is stateless, so stateless microservices are well understood and are easy to manage, but that rendezvous service isn't stateless. It actually has a state. Because when you think about it, when a request comes in and you need to wait for all the scores, it's a little bit like a mailbox. So there's like that evaluation service which has mailboxes waiting for their scores to come back in. So in SQL, it's like a group by operation. So there's clearly a state there. And so we have all these scores coming in. We need to distribute them to their correct mailbox where we have a policy running, deciding what to do with the scores coming in. One way to do that, right, is just to subscribe every mailbox to that message stream. But it means that every single policy has to evaluate and filter every single message coming through. That doesn't scale very well. If you have a lot of open requests running in parallel, this is extremely expensive, in particular if you have a lot of models running too. So you need to have something where you can basically have some kind of fan out of the scores to the corresponding requests. And the way we did that is like a sidecar of a score collection service, which actually subscribes to the stream. And every single time a request comes in, we attach an ID of that mailbox it's associated with. And that is a Unix socket on a shared volume between the evaluation service and the collection service. So we can actually use Unix sockets and Unix socket servers to actually communicate between the collection service and the evaluation service and do the fan out. That might sound a little bit abstract. There's an article which has code, which makes it a little bit more obvious. But basically, there is a way to actually build a kind of fan out in that kind of stateful rendezvous service without having to pay heavy penalties for the filtering of these scores. So what a lot of people ask after they hear all of that and nod is like, so what's the overhead? You know, you saw the architecture has a lot of streams, a lot of different services, and it's obviously important that this is performant enough that you can actually, that you have time to score, that you can evaluate your neural network within your SLA you just, you know, wanted to implement with your fancy architecture. So currently the implementation has an overhead for the entire round trip of all the rendezvous architecture specific components of like 40 to 50 milliseconds. And this gives you a lot of time to score a request. So it works pretty well, it's very performant. And down here, this is like a load balancing test of the environment running on my laptop. And you see my laptop can easily handle 100 requests flowing through that without really sweating while it's also playing Spotify. So the architecture itself works very well, and the kind of cost to really do it right, 40 to 50 milliseconds, is quite small when you consider how much you get. So yeah, so that's been it. There are the necessary credits. So Ted Dunning and Alan Friedman, they wrote that inspirational book, Machine Learning Logistics. There's a free ebook on their homepage, on the MapR homepage, and you should read it because actually rendezvous architecture is just one chapter of that entire book. It really changed how I see data science in production. Terry and Chris, they've been around for a while helping me while businesses didn't really support the idea, advancing it, etc. They've been early day believers, so I'm always really grateful for their support. And as I mentioned, I wrote an article on Towards Data Science about it, which also has a little bit of code in it, etc., and more details. And I recommend you to just have a read through that, or just ask me questions.